minus the root of minus the determinant of the induced metric, and then the term that we will add here is the trace of the extrinsic curvature K. And this made the action for gravity to be well posed, so it has a nice variational principle, and at the same time, when we vary with respect to the metric,
before you proceed, could you expand a little more on extrinsic curvature, like this K term? Like, we know the Riemann tensor has a nice interpretation. So, but what is the interpretation for this extrinsic curvature?
Yeah, I will talk about it. I will talk about it in a little bit when we do the black hole. So let's postpone that. But in 2 words, it's the scalar that you can build for a surface or a submanifold embedded in a larger manifold. Again, what should come here is some scalar quantity now at the boundary, but the boundary is embedded in your full space-time. So we will see in a second you have your cigar geometry, and you want to see what happens at the boundary of it. And so there's this nice quantity that you can define once that you define a normal vector to the surface. So in order for the extrinsic curvature to appear, you need the surface to be embedded in a higher dimensional one so that you can define this null vector. But I will do the calculation precisely in a second. Is that okay?
Yes.
Okay. All right, and we said that boundary terms, local boundary terms, anyways, do not affect the equations of motion. So if we vary the action with respect to the inverse metric, what we will get is just the vacuum Einstein equation. And in all this discussion, we decided to never talk about matter. So there's no stress energy tensor in the discussion. Okay, great. So we are almost there. We already have G Newton in the game. So now, what's the area of horizon? We said that one of the solutions to the theory of general relativity at the classical level is the Schwarzschild black hole metric. And it can be given by this line element. And we discussed, not as much as I would like to, but we discussed at least some properties of this metric, including the idea of the Penrose diagram. So this metric has T that goes from minus infinity to infinity, R that goes 0 to infinity, and then the 2 angles that are just bounded. But these 2 coordinates extend all the way to infinity, so it's hard to visualize this black hole because it has infinite volume. But nevertheless, we can play with this idea of Penrose diagrams, at least to see the causal structure of the manifold. And we discussed that this black hole can be drawn as something like this. So these surfaces of null surfaces over here were infinity. The property of this diagram is that light travels at 45 degrees. And then this diagram has some special surfaces, one of which is r equals 2 g Newton. That's the radius of the horizon. Let's call it RH. And then there's something strange happening when r goes to infinity, where scalar quantities diverge. We don't know what happens to the theory of general relativity at those points, and we call those singularity, and I'm just doing wiggly lines because I don't know what's happening in there. And so we discussed that by looking at this diagram, if you were some light, or if you were a particle inside the black hole, like I'm doing this dot over here, and I draw my light cone, the only possibility for me is to end up at r equal to 0, and I go with that would take going outside my light cone, and that's not allowed by causality. Instead, if I stay outside the black hole, it's true that I can go from minus infinity to infinity. Time in this diagram goes something like this. So time grows with these lines over here. Okay? Okay, so let's discuss a little bit what AH is. This is what appears in the entropy formula, but we haven't discussed it so far. So area, this is the area of the horizon. So the idea is you pick a constant time slice, say, just for simplicity, we can say t equals 0, and then we have the horizon sitting at r equals to RH, and what we want to compute is the area of the horizon. That should be an area over the angular variables, I d theta, of just RH squared sine squared theta, and that's it. Okay, so the phi integral is very easy to do. It just gives 2 pi. The RH squared is easy to do. We just leave RH squared. And we are left with this theta integral. So who can tell me what's the integral of sine squared theta from 0 to pi? I'm doing things properly, no?
I think you wrote 0 to theta. It should be pi.
Oh, yes, sorry, thanks. Please keep your eyes awake. No one?
It's
Okay,
pi
that gives
over
pi
2.
over 2. Yeah, it's pi over 2. So what am I doing wrong? It looks like I'm doing something wrong. Well, up to pi's. I think I wanted to get 4 pi squared. RH. No, because the other comes from, let's see. Yeah. Yeah, so then I have 2 pi times pi over 2 times, 2mg squared. So the 2 cancel, and I get 4 pi squared m squared g Newton squared. Okay? So area of the horizon is nothing more than basically the mass of the black hole squared. Okay? So now the goal, for some reason, I can't see your share screen. Can someone help Hamas?
I think it's a problem at Hamas's end because I can, see the
Yeah.
both the screens.
Hamas, can you rejoin?
Actually, Hamas has, I think he has tried rejoining also. Hamas,
In
can
that
you?
case, I would ask him to quit the browser and restart the browser.
Yeah, Hamas, you can, try using a different browser maybe or a different device. Because I think rest of us, Taha and rest of us, we can, we are able to see both the video as well as the Damien's writing device. So, but Hamas, I would like to tell you that I'm making a video recording also, so you can see that later also. So yes, Damien, you can continue.
I think he left anyways. Okay, so now we have all the quantities at our disposal. The goal is to show you now that if we apply the rules of StatMech to gravity, then we will find that entropy is area over 4G Newton. Okay? That's the goal of today. Are there questions so far? This is just a summary so that you don't think that during the last week I've been just going around random concepts because I wanted to torture you. This was planned so that we can understand this formula at the very end.
Yes.
But this formula again seems easy, but it has lots of different concepts attached to it, so I needed to explain that to you in order to derive this formula.
And we are in natural units, right?
Sorry?
I asked if we are in natural units right now because I don't see a C, K, B, or H bar.
Yeah. So at the very beginning of the class, I said today these are the units I will be considering. Okay, so now let's try to do that. We said, okay, now let's go to space-time statistical mechanics. This is what we started discussing yesterday. We said that the basic object to study in the canonical ensemble is the partition function of canonical ensemble. Sorry. Partition function Z, and in order to compute Z, we found that a useful way of doing that is to path integrate, whatever this means, the metric, and then weight the different metrics in this path integral by the value of its Euclidean action for that particular metric. Okay? If we manage to do this, we will have the whole partition function for the theory of quantum gravity, because in the very same way as Tibra was doing, this formulation of quantum mechanics or quantum theory basically allows to go beyond the classical solution, that are solutions to the equation of motion, and start summing over all possible ways or all possible metrics that are available. Okay, so before we go on, I need to again warn you that we have no idea of what this object is. Okay? Z quantum gravity is complicated. If we knew how to compute this, we would be more or less done. We would have a theory of Euclidean quantum gravity, at least. That would be a major accomplishment in theoretical physics. But unfortunately, we don't know how to do this in full generality. So let me tell you some of the confusions that can appear when we try to evaluate this object. So the first one is, of course, what is the G? What should we sum over? Okay? So the theory of GR is a theory that has diffeos. I don't want to become very technical, but you know what this means, right? If we just have a metric and we do some coordinate change, x to y of x, we are not doing anything to the metric, right? We are just changing the way in which we describe it. So in this sense, G and G tilde are the same metric. And so this dg over here should be summing over inequivalent metrics. Inequivalent metrics. Okay? Now the task of being able to differentiate whether two metrics are or not the same is a hard task that in principle can be done. It's easier to do in lower dimensions, but it gets more and more complicated as we go into higher dimensions. This problem is not completely unknown to theoretical physics. It's very similar to what happens to Maxwell theory or to any gauge theory in general. When you have some gauge redundancy, if you want to do a path integral, you need to be very careful because you don't want to count twice the same solution. Okay? So that's one problem this has. The other problem related to summing is topology. We have an expert here in the audience. Should we sum over topologies when we do this theory of quantum gravity? So let's say that at the boundary we have some circle, and then we want to compute metrics that satisfy the Einstein equation inside. Should we include things like this, but also things like this when we have a hole inside, or when we have some, let's try to do it, we have a handle. Should we take into account these things in the gravitational path integral, and if so, how do we do it in the proper way? Again, these questions can be attacked in lower dimensions where the theory becomes more topological, so that it's easier to classify manifolds, Euclidean manifolds by topology, but it's usually a very, very hard question in the context of higher dimensions. In particular because if you go back now to the Lorentzian theory, you should have some dynamics, and you should find a way of going from a black hole with trivial topology to some formation of a hole in the middle space-time and changing the topology of it in a dynamical way. We have no idea how to do that, how to describe that process in real time. So complicated. It's also most probably infinite. So we know that gravity is a non-renormalizable theory, but here we can see it very clearly because the Euclidean action, so minus SE, is just 1 over 16 pi g Newton without the boundary term. I will just write it very schematically as GR. And you can always try to find, or you can always find manifolds that are huge, that their volume tends to infinity. And so this term over here will just grow to infinity, and then when we sum the contribution to the path integral of that metric will be huge, even if it doesn't satisfy the Einstein equation.
You have a negative sign there, right? With the Euclidean action. So if this term goes up...
I have a minus. Yeah, I have two minus signs. So the Euclidean action has a minus sign, and then I have to evaluate e to the minus SE.
Oh, yeah, I see.
And so this is a very complicated problem. It goes under the name of the conformal factor problem. And there are ways of going around it, but the standard solution, I don't know how in detail I need to go into this, but I will just tell you to convince you that this is really an ugly object. The standard solution requires complexifying the contour of integration. So all of a sudden, we need to, this is something that it was done by Tibra's supervisor. This goes by the name of Gibbons, Hawking, and Perry. But all of a sudden, if we are studying the Euclidean path integral, what this thing is telling us is that we should not only consider real metrics, but we should get into the world of complex metrics. And this is a disaster, right? Should we sum over, well, yeah, what are the rules? Now, not only in the real plane, in the real space of metrics, but in the complex space of metrics. Yeah, so conclusion about these 5 minutes, this is hard. And most probably not even well defined in whole generality. Okay. However, we can still make some progress in certain limits. Go ahead.
What are the limits of the integral over here? So is it still dependent on time, as in on the initial metric and the final metric at some time?
Where? In here, you mean?
In the path integral.
Yeah, so the path integral is a path integral over metrics. So let me just address that. It's a good question. So this is a path integral where I should sum over all metrics that satisfy certain boundary condition. So I'm in Euclidean space, I'm summing over smooth manifolds right? The smooth manifolds that end up in a particular way. So for instance, I can say, I want my boundary conditions to be that the three-dimensional metric is S1 cross S2, for instance. Or I can say, I want my boundary conditions to be S1 cross the torus, T2. Choice, different choices of boundary conditions, right? Boundary conditions are part of the definition of the theory. So what we will do in a minute is to argue that in order to do thermodynamics in the canonical ensemble, what we will need to do is to put boundary conditions that are S1 cross S2. Is this clear, or? I mean, I will do it more carefully in a second, but is the idea clear? So in order to define the theory, you need to define its action, well, its degrees of freedom, then its action, and then its boundary conditions. That completely defines a theory for us. It's not enough to define just the action. In gravity, it will be the same. We need to define a boundary for this.
That's why we needed that other
Euclidean action.
Taha, can you say what you said again?
I said that's why we needed the other term, like the Gibbons-Hawking-York term. Like we need a boundary condition to define.
Exactly. So I was imposing, I was making you suffer a little more than usual to include that boundary term, because I knew that that's important in order to define the Euclidean theory properly. It also appears in Lorentzian signature, of course, and it's important, but it will have more and more relevance in this context. Okay? Is it clear?
What I'm still a little confused about is the boundary term that we include is a boundary in space-time. But when we integrate over, or we carry out this path integral, that should be a boundary in time. As in, when you talk about.
Yeah, but this is a path integral. It's what Tibra was.
Can I interject a little bit?
Yeah.
So I think something that you did, Damian, yesterday, and Hamas may have just missed it, is that when you go from quantum mechanics to quantum field theory, or field theory in general, and in principle we are doing some sort of quantum field theory here, the role of time in quantum mechanics, which is just a parameter, becomes is in quantum field theory, it's time and space coordinates which take on that role. And the role of the position operator, of the position, which is an observable in quantum mechanics, is taken on by the fields. So I think what Hamas is saying is that in quantum mechanics, we have seen that the boundary conditions are specified at T0 and T final, Ti and T final. Here, I think he's asking, what are the boundary conditions that we have on, say, the in the argument of the G? Is that something, Hamas, is that what you're asking?
Yeah, so we kind of fix position at certain times, right? So in the case of field theories, what we'll do is we'll fix the fields at all space-time coordinates. So it kind of defines the boundary surface.
Hamas, does that answer your question?
Yeah,
it does.
We can also discuss it afterwards in the problem-solving session. But the idea here in these path integrals is that we impose some boundary condition for the metric, whatever it has to be Dirichlet boundary conditions because of the way in which we define the action. And then we should sum over all possible metrics that have that satisfy this boundary condition. Okay? The boundary is well, I haven't defined where is the boundary yet, so you will see in a second, maybe in an example it will become much clearer. But we don't need to define where is it. We just need to say that there's a boundary that is S1 cross S2, and then gravity will do the job for us. But yeah, let's just proceed, and you will see in this example that is very simple. Okay, so now what I need to tell you is that we have the Euclidean path integral, the Euclidean action, sorry, and I will stop writing with a lot of detail because if not I will never get where I want. Root HK. And the idea is that in general, this will be very complicated, but luckily for us, we have a G Newton appearing here. And G Newton is kind of the strength of the gravitational interaction. And we can think about the path integral in the limit where G Newton goes to 0. Okay, when G Newton goes to 0, the gravitational interactions are small. You can assume, right, if we have e to the minus se, and the action is going to infinity, we can think that this action will be simplified in that limit. So I think Tibra will talk about this in the next lecture in more generality. Is that true, Tibra? Not for gravity, but in general.
Yes, the semi-classical limit, yes.
Yeah. So what I'm going to say very, very fast, and this I will ask you to believe me, and if not, we discuss it over the problem zone. I will do a single integral. So say that I want to do a Gaussian integral, or not a Gaussian integral, but I do some integral of dx of e to the minus sx. This is not a path integral, and I want to integrate over all x's. Okay, this is not a path integral, it's an integral over some function s that depends on a parameter x. And one thing we can do is to expand this function around some point. So we can do s of x is approximately s at x equals x naught plus dx evaluated at x equals x naught, x minus x naught, plus ds squared, dx squared, x equals x naught, x minus x naught squared, maybe over 2. Okay, and this is the Taylor series expansion for this function. Now something funny happens if we choose the x naught such that this first term vanishes. So if we assume that x, so now the idea is that if we look at x naught such that this term vanishes, the main contribution from all this function will come from this leading term. And this term, because it has an x minus x naught squared, will be very, very subtracted in this integral that has e to the minus s of x. Okay, so the claim is the integral will do this properly. This part you can even integrate it because it's a Gaussian integral, so we can find a better answer for this, but at least to leading order, particularly if we have a parameter alpha here that gets very, very large, this function over here becomes very, very peaked around some value. And in the limit of this alpha being very large, we can simplify this or approximate this by basically e to the minus alpha s at x equals x naught. Okay? And this is very, very sketchy, and I will wait for Tibra to do his part on this later. But now we will do something very similar, but now for a path integral. We will say that if we have our gravitational path integral now, e to the minus s of g, in the limit where g Newton goes to 0, we will approximate this thing by just e to the minus s evaluated in x naught, that now x naught will be g naught. That g naught has the property that delta s delta g is equal to 0. So basically a solution to the Einstein equation. Okay? If the Einstein equation has more than one solution, the recipe is to sum overall solutions. Okay? This is a trick to approximate functions of this type where you have a large parameter. It's called a saddle approximation. I don't know, maybe you've seen it in some, so sometimes it's taught in some mathematical methods or some course like this, or in quantum field theory, if you took some advanced module that includes the path integral. But the idea again is that if you have a parameter that is very small or very big, there's a way of approximating these path integrals, but by just computing the value of the action at the solution.
If I'm not wrong, I think it is an optimization technique, or not related to optimization.
Yes, so some people, yeah, it is related because, so the idea is how to approximate functions that are like this one.
Okay.
The idea is that, so you don't need to know everything about the function in order to approximate this integral. So the function might be very complicated, but because it decays exponentially, all the features of the function s at very large x will be exponentially suppressed.
Yes.
So you don't need, they are not very important. Everything will be dominated by the saddle point, by x naught.
Yes.
Because the function just decays exponentially. Yeah, so I did this very, very bad, but so this is supposed to be x naught, this is x, and this is f of x. S of x, right? And if this going down is very, very sharp, most of the area will come from very close to x naught. All the area that's in here, even if the function is doing crazy things, it doesn't matter because it will integrate to something much less than this part. Okay?
Yes.
That's the idea. again, if you don't believe me, and you shouldn't, we can do some exercises during the problem session or afterwards, so that you can convince yourself that this is an appropriate thing to do. It's an approximation again, but it's an approximation that will work very nicely in powers of alpha, or inverse powers of alpha. Okay, so now let's do that for our black hole solution. We have a solution to the so let me write it down. So the Euclidean black hole solution is a solution to delta S E delta G mu nu equals 0. So we can consider the limit of G Newton going to 0 and do the saddle point approximation for gravity. Okay, so now S black hole, let's call it, it's approximately E to the minus S E evaluated at the G black hole metric. This is only valid in the G Newton going to 0 limit. Are there questions? Is this clear? I'm not asking you to completely understand what I'm doing, but at least the rationale before this analysis is clear. The detail probably you will need to digest a little bit, but the idea is that we're doing a hard path integral. We are taking the semi-classical limit where the gravitational interactions are suppressed, and so we can approximate the whole partition function or path integral by the value of the action at a solution of the Einstein equation. That's the logic of what I'm trying to do here. Okay. So then let's bring the black hole metric back into the game, because so far we haven't talked too much about the Euclidean black hole solution. So this is d squared equals minus 1 minus 2 mg over r, the tau Euclidean squared with a plus here, plus dr squared over 1 minus 2 mg over r, plus r squared d omega squared. Okay? And we discussed yesterday that this is a 4-dimensional manifold, and if we look it in the tau Euclidean R plane, this looks like a cigar geometry. We were doing it like this, where each point in this 2-dimensional each point in this 2-dimensional diagram should be supplemented by a 2-dimensional sphere that is infinitely large as r goes to infinity and starts decreasing until it has radius rh at the position of the horizon. Okay, this is what we discussed yesterday, but no one complained that why I was writing this in this very nice, smooth way, because I could also have written something like this. This is also a two-dimensional manifold. At each constant r, it has a circle, but now it looks more like a cone than a cigar. And the difference between these two is what's happening very close to the horizon. Okay? And so I will now spend a little bit of time trying to convince you that in order to have a smooth manifold, we will need the period of the tau to be very particular in order to avoid problems that might come from being non-smooth close to the position of the horizon, that now it's just 1 point.
So, I mean, Damien, that
Okay.
diffeomorphism,
Yes.
like diffeomorphism doesn't guarantee that everything will be smooth.
No, it doesn't. So this metric is assuming that TE is periodic with period beta. So you should identify TE with with TE plus beta. Okay, but I'm not telling you what this beta is so far. And it turns out that we are not free to choose this in gravity. In order for this manifold to be smooth and not have any problem close to the black hole horizon, we need this beta to be a very particular function. Yeah.
Right.
Okay. So let me try to do that. So now let's consider this metric. Let's look at this metric. Very close to R equals 2mg. Okay, so I can define the coordinate now. I will do a change of coordinates, maybe rho, that is R minus 2mg Newton, and I will consider the limit where rho is very small. Let me just look for the normalization factors so that I don't make a mess here. Yeah, so why? I think what I want to do is to define this as rho squared. Sorry, I had this in the iPad. Well, let me try to find it. So give me 1 second. I wanted to come here. Oh yeah, root h. Oh. How do I find my node now? Oops. What am I doing? Do you know how I go back to unfile favorite recent?
Well, it appears these are the recent files.
No, but I want the one I was writing right now into.
Okay, the one
It shouldn't be,
you were using Notability or GoodNotes?
Yeah,
Well, there's one.
no, Notability.
Notability, then go to
Go
the
to all nodes, yeah.
and go to the app. Like
No.
go to the Notability app. So
Go to all nodes.
Isn't
In the
this one?
unfiled nodes, in top on the left,
All nodes.
And yeah, the top one is the one you're working on.
This one. Ah,
Yeah.
thanks. Sorry. Yeah, if I were on the whiteboard, I would do this, and I don't need the iPad to write on. Okay, so let's define this in this way now. Just give me 1 second. No, I'm trying to look for this. Okay, and now I want to expand these functions over here, this one and this one, for rho squared much less than 1. Right, so the metric will be something like now plus 1 plus 2mg over, and instead of r, I will write rho squared plus 2mg d tau e squared, and here I will have to write something that at least schematically, you will need to do the change of coordinates, but you will see. So rho squared is r, so dr is 2 rho. So there will be a 2 rho squared, there will be a d rho squared appearing here, up to some function again here, plus, and here it will be rh squared d omega. Okay, so this is homework. Homework.
Damian, can you
That if you
go
yes.
back to the landscape mode?
Oh yeah, sorry.
Thank you.
Here we are. Check that if you expand this for rho much less than 1, get something like rho squared d squared, or d, let's call it, sorry, the theta squared plus the rho squared plus rh squared the omega squared. This is approximately in the leading order of rho being small. Yeah, sorry, okay, anyways. So the claim is that now, if you look at this metric over here, it looks pretty much as the plane in spherical coordinates. Okay, is this clear?
Yes.
I mean, up to you doing this calculation. Let me try to find you here so I can see if anyone is speaking. Yeah. Okay. So this is like the plane, but in order for this to be the plane, the smooth plane, we need that this theta.
This is a reminder. Water after every 4 hours.
The case, we will have something like a plane, but where when you do a full cycle, you will get that the manifold will not close in a smooth way. So there will be a conical singularity at the origin at rho equals 0 if theta is not periodic with period 2 pi.
This is written?
This is going a bit slow, at least in my screen, so I just drew that diagram like 20 seconds ago.
Yes, it's appearing okay.
Okay, but if there are no complaints, I will continue. Okay, so the idea is that in order for this to be a regular metric close to rho equals to 0, then theta has to have periodicity 2 pi. Again, I'm sure that in the whiteboard this will be much more clear, so apologies for this, but believe me. And so now we should go back. If theta is just a function of the Euclidean time, so if theta goes to theta plus 2 pi, this will mean that theta, tau e, will also need to be periodic. And here I will just put the result, and you can check it. And in fact, I put this as the first problem in the new problem sheet. You can check that this period has to be 8 pi m. Okay? But we said before that Euclidean time has to be periodic in our thermodynamical explorations, had to be periodic with period beta. So we just found by doing this Euclidean voodoo and asking for smoothness of the metric that beta of the black hole is equal to 8 pi m, the mass of the black hole, in these units. This is the same that Hawking, this is identical to Hawking's temperature. So if you ever visit London, Stephen Hawking is buried in Westminster Abbey, where all the famous British characters are buried. And you can see that you will see something like this formula in the floor on top of where he's buried. The formula will not be in terms of beta, but it will be in terms of T. So it will be something like T equals 1 over m with all the right constants. You can look the photo in Wikipedia as well. Okay, so after this detour, I think we are finally in position to do our calculation, that is the partition function of the Schwarzschild black hole metric. So what we need to do is to evaluate the action in this black hole metric, the Euclidean action. So let's write down the Euclidean action. SE is equal to minus 1 over 16 pi g Newton, d for x root g r, minus 1 over 8 pi g Newton, d3x root h k. And we need to evaluate this for this metric. Plus 1 minus 2 mg over r d tau e squared plus d r squared. For r going from RH to, let's call it r boundary, and Euclidean time going from 0 to beta. But now we know what's RH and what's beta, and we just need to decide what RB is, the boundary of our space. But let's do that just in a second. So there's something easier to highlight first. So who can tell me what this term over here gives if I evaluate it? If I evaluate this in the black hole metric, what do we get for this term? So what is R for G black hole? Someone?
There is no matter, right?
There's no matter.
0.
And the black hole, 0, right? R for the black hole metric is equal to 0 because the black hole metric satisfies the Einstein equation. So the term in yellow has to be 0. And so you can see now why I needed to have the boundary term, because if not, my whole Euclidean action will be just 0, and my partition function will be e to the 0, that is just 1. There will not be any beta, there will not be any temperature, there won't be any energy, there won't be anything. There will be a constant partition function that is not what we want. So it is crucial in this gravitational computation to have a boundary and compute this term, because in fact everything that we want will come from the boundary term. So let's look at that boundary term a little bit closer, and I will now address the question that was raised before of what is this K. So now let's go back to our cigar geometry. I will do it a little bit more specific to this geometry, because if not, I think I have only 10 minutes or so, because Imran always allows me to go overtime. So if not, I will never finish. So the idea is now I will cut my cigar geometry at some R equals to RB. Okay? This RB, this surface, well, we also have a two sphere there, but will be described by a vector and mu that is normal to the surface. And the formal definition of K mu nu, is what we call extrinsic curvature. Extrinsic curvature is just the covariant derivative of the normal unit vector at the boundary. Okay, this thing over here is the normal unit vector at the boundary. But now there's a trick, because the only thing we care about is root h times k. And there's a trick to compute this that you will prove as homework, that says that you can actually do something like, n mu d mu of root h. Okay, this is exercise, but the normal vector here in this case is very easy to find, right? Because the normal vector of a constant R surface should just point in the R direction, right? This is R, or minus R, I don't know. We need to normalize this properly. I'm going a bit fast, because if not, I will not get to the end. It's clear that the normal vector to a constant R surface points in the R direction.
So for a short-shelled black hole, will the derivative of these normal vector with respect will only be non-zero with respect to theta and phi, right? Like with respect to r and with respect to time, it should be 0.
What are you asking? Is it zero, this thing, or what?
I mean, I'm asking, you said the extrinsic curvature, this thing is basically the covariant derivative of normal vector.
Yeah,
So,
yeah.
If I take the derivative of normal vector with respect to 4 different coordinates like r, t, theta, and phi. So for
Yeah.
short-shaped black hole, I'm expecting that the only derivative that will be non-zero will be with respect to angular coordinates, right?
No, that's not completely correct because the normal vector has to be normalized. And so in order to normalize this, you need n mu being 1. So you will need to include a metric here. Okay? And this will tell you that the norm of n, because G has factors of r, the normal vector will also have factors of r in here. So I don't want to write it because I don't remember the normalization, but I think it's something like this. So then when you take derivatives with respect to r of this thing, you will get some other dependence in k as well. But you will need to evaluate that at the boundary. Yeah, so this is an exercise. But these formulas assume that the normal vector has unit norm, and so in that norm, r can appear explicitly. Okay. Okay. So, yeah. Okay, so let me tell you directly the result because if not, we will never make it. The claim is that root hk for the black hole at r equals rb is equal to 2rb minus 3m. Okay, so now let's put it back on the Euclidean action. Now SE is minus 1 over 8 pi g Newton. I already removed the 0 that appears from the back term. And I have a boundary term that now has theta from 0 to pi, d phi from 0 to 2 pi, tau from 0 to beta. And instead of root hk, I will just write 2rb minus 3m. And I need to remember that the Jacobian for this d theta comes with a sign of theta inside. Okay. And so now I can do this calculation. They are all very simple integrals. And I will get that the Euclidean action, not the entropy, but the Euclidean action is minus, let's see, I think it's minus beta over 8 pi g Newton. Sorry, I'm just doing this because I don't have my notes, so I don't have the answer. And there should be something, yeah, I think, well, up to some constant, I think it's a 2 appearing here. So check, but up to a number, this is the answer for the Euclidean action. But now we don't want only the Euclidean action. You see, it's written in terms of beta and m. But we don't want beta and m because we know that m and beta are related by beta is equal to 8 pi m g Newton? No, 8 pi m. Let's look at it somewhere here, where 8 pi m here. So let's write it down properly. SE as a function of beta is equal to minus beta over 16 pi g Newton to RB minus 3 beta over 8 pi g Newton. Okay, and let's write it down again. This term will be minus beta RB over 8 pi g Newton plus beta squared over g Newton squared times some numbers here that I will leave them for homework. Okay, so now we found our partition function for gravity. Said black hole is equal to E to the minus S E. And normally I would start doing something like computing beta F by doing log of Z, and then I can keep computing things. But because I'm very, very late with time, I will just compute the entropy of the black hole as a function of beta. So if you go back to my computations from yesterday, you will see that what I need to do is to do 1 minus beta d beta of log Z. That's the conclusion from yesterday, or minus, or whatever. So log Z is minus SE. So minus SE is equal to minus beta RB over 8 pi G plus this number, let's call this number alpha black hole, beta squared over G Newton squared. Okay, but I have the minus sign, so let me do this properly. So this one will become plus and this one will become minus. And let's do beta d beta of minus SE. So this first term over here is proportional to beta. So when I take derivative of beta, I will get just this term times beta, I will get the same term. Beta RB over 8 pi G. This one, it will be the same, but I will get an extra 2, right? So beta, d beta of beta squared is just 2 beta times beta, I get 2 times beta squared. So here is alpha black hole, beta squared over G Newton squared. And now let's do 1. Sorry, Imran, I'm finishing very soon. It's almost there.
Yes.
You can feel it, right? 1 minus beta d beta, we get beta RB over 8 pi G Newton minus beta RB over 8 pi G Newton. The first contribution from here cancels, so all the dependence on the boundary goes away. I don't care for the entropy, where's the position of this boundary. And then I get 1 minus beta d beta, I get alpha black hole beta squared over G Newton squared. Here there's a 2. Right? So there's a minus here, and now I have plus, because of this minus minus, 2 times alpha black hole beta squared over G Newton squared. G Newton squared. I have a problem with the units now. What's going on? What's going on? Oh yeah, this is wrong, right? Why am I putting here G Newton squared? Sorry about that. Oops. So this should be only G Newton, I think. Because there's no, yeah, there's G Newton here, so I should remove these two, and now these two, yes. And now there we go. So this is equal to alpha b, there's minus plus 2, so I get plus 1. Beta squared, this is also over G Newton. But beta squared is nothing more than alpha beta h, this is 8 pi m squared over G Newton. And so basically this gives that S black hole is equal, as promised, alpha beta h 64 pi squared m squared over G Newton. And so if I would have been careful and kept track of all my constants, the claim is that this thing will be just 4 pi squared, and you will have you will have get back that the entropy of the black hole is the area of the horizon over 4 G Newton. Okay, so I'm very much over time. I have 20,000 more things to say about this formula, but let's close it here. So let's recap.
Yes.
We started with the Euclidean partition function for gravity. We approximated that by e to the minus s Euclidean, evaluated at the black hole metric. We computed this for the black hole, and then from here we use just StatMech to compute entropy, as we know that we should do in the canonical ensemble, and we recovered that this should be the area of the black hole over 4G. Okay, so using this idea of Euclidean methods to study StatMech, we found both that black holes have a temperature that is proportional to 1 over the mass of the black hole, and that they have entropy proportional to the area of its horizon. So this could be like m squared over G Newton. Okay? You might not trust these Euclidean methods, and again, you shouldn't. But the idea is that this was also backed up by actual calculations in Lorentzian signature, such as the one that Hawking did for the Hawking radiation, that gave a Lorentzian interpretation of the temperature of the black hole in terms of radiation that an observer is collecting at infinity. Okay? So, yeah, sorry this was not as clear as yesterday, but I cannot see my own notes in the iPad. But I hope you got an idea of how black hole dynamics work and how powerful these methods are. So, because I'm finishing here, let me finish with one homework question. What are the black hole microstates that account for this entropy. And I finish here. Thanks. I'm sorry for the delay.
All right. No, at least you finished the lecture, so that's great. So now usually we have the time for tea break, and we usually combine discussions with tea break. So now virtually we don't have any tea, but we can have questions. So Hamas, Taha, Hinza, Hira, do you have any question?
This last question, like, is it in the problem sheet or what?
This question about the microstate.
Sorry,
so-
but
Yeah, this one.
that question, if you solve that question, you win a Nobel Prize.
That's what I was wondering, like, entropy, just knowing what it means to have an entropy, like, it seems weird, like, why would black hole have an entropy?
Why would black holes have an entropy? Well, you can ask the same question about a piece of liquid or water. You can ask why will a liquid have entropy? And then we know the answer to that. You will tell me, because if you put a piece of water in the microscope, you will see that it's made of molecules, and then we can count the number of molecules, the number of configurations of molecules at different speeds, and we can get an entropy out of at microscopic counting. Yeah, so Tibra raised the hand, so let me finish this and then I let Tibra speak. And so now, of course, for gravity, we don't know what are the microstates of gravity, but we can do these experiments. And we can see that if all this makes sense, then it means that gravity is also made of microstates. It's just that we don't know what the molecules of gravity are in general. In this particular case, we don't even know it because the black hole is evaporating, and if you wait long enough, this is not a stable configuration. If you compute the specific heat for this black hole, you will see that it's negative. So it's very, very hard to imagine what are the molecules of this black hole. But there are other black holes that are stable and in which we have a better idea of what are the molecules, the microscopic molecules of this space-time. So if you have a black hole in ADS, you will see this in the problem 2 of your problem sheet if you try to do it. You will see that black holes, some black holes in ADS have positive specific heat, so they are stable. So they are really like a piece of liquid inside the glass. And so you can compute that entropy, and you can see how the entropy scales with, say, temperature, and you can realize that that entropy is exactly the same entropy of a theory, a particular quantum field theory that is conformal, and it lives in one less dimension. Okay? So if you look at those black holes in ADS, and you compute their thermodynamics, you might have predicted that the microscopic atoms of that space-time are nothing more than a quantum field, the atoms of a quantum field theory in one lower dimensions, and you will have rediscovered the ADS-CFT correspondence. Okay, so for this particular black hole, we don't have that picture, but my claim is that at least in other cases, it helped us understanding what are the microscopic degrees of freedom. In the case of an ADS black hole, this same computation gives exactly the same entropy that you would get in a conformal field theory at fine temperature in one lower dimension. I don't know if this answers the question. Of course, this is just one number, so then you need to work harder in order to establish.
I mean, it seems
the
we're back
precise
in the
relation.
19th century. I mean, it seems
Clear that?
it seems we're back in the 19th century. Like, we have computed that there is something called temperature, but we don't know what it's made of. Like, what are the microstates? Like, you know, back then there was no concept of atoms, so we didn't know what temperature.
Yeah, exactly. Yeah, so we are in the same stage as with gravity, as scientists, Lord Kelvin and Boyle and Charles, they were at the end of the 1900s. We are doing experiments with thermodynamics. We are finding interesting formulas regarding space-time and thermodynamics, and we are trying to use them to do something like StatMech and finding the microscopic structure of gravity that we believe there should be some, at least in some cases, there should be some microscopic interpretation of gravity. But we are, as you are saying, at the same stage or level as Kelvin was at the beginning of the 20th century. We are doing experiments, thought experiments, and these methods allow us to gather information about how gravity should behave in different contexts. You could add charge, you can add angular momentum, you can change the type of black holes, you can go to higher dimensions, lower dimensions, and all that are the experiments we can do in order to try to find the microscopic atoms of space-time.
So does this kind of also answer the question that why there needs to be a theory of quantum gravity? Like, you know, there have been people who have asked, like, what if there is no quantum theory of gravity? But this question, it seems like there must be some theory of quantum gravity. So does this answer those people that we definitely need a theory of quantum gravity? Like, gravity have to be something?
Yes and no. I would say that these calculations are giving strong evidence of an underlying microscopic theory. But of course, you can always try to hook up some weird theory where this is not actually microscopic counting of microstates, but is some classical noise or weird things like that. But yeah, in my opinion, and I guess it's the opinion of, the majority of the field in which I work in, this is pointing towards strong evidence of a theory of quantum gravity that we might not completely know in all cases, but that we might make progress by doing this type of experiments. Entropy is a complicated object, so yeah, because it measures we haven't discussed this so much, but it also measures that there are entropies that measure the level of uncertainty of what we don't know about the system. Like when Tibra was writing these pure states, we were tracing out part of the state and then we were getting entanglement entropy. This entropy is counting the fact that we don't know about the rest of the system. So you can always try to find some weird classical theory where you don't know everything about the theory, so there's some classical uncertainty, and maybe this entropy is counting that. But okay, I like to believe in the most natural explanation of things. That's usually how physics works. And the most natural explanation of all these calculations is that there should be some microscopic quantum theory of gravity that has some thermodynamical behavior. And yeah, is it clear? I don't know, Tibra, you have some comments?
I had a question. So,
Yeah.
if you think of the formation of a black hole as a physical process, then it is
Yeah.
comes from the collapse of some massive star.
Yes.
And we can assign some entropy to the star as it is collapsing, I presume. Like, even if you can't really calculate
Yes.
it exactly, we can probably do an order of magnitude calculation, right? And then
Yes.
once that star has become a black hole, because we know its mass, so we can use the Schwarzschild metric and this technique to kind of compute the Beakenstein-Hawking entropy. So my question is there a correspondence between these two numbers? And if so, does the Beakenstein-Hawking entropy correspond to the entropy of the collapsing star?
It's a very good question. It's a harder question because now we are in a dynamical setting. So all these, I think, Euclidean techniques are not useful anymore. So you have to come out with a definition of entropy that is dynamical and it changes with time, right? So that's the first.
Right.
The first comment. This is not always easy to do in gravity. As far as I know, nevertheless, people do these types of analysis. Usually they require numerical relativity. I think in the context of ADS-CFT, you can actually do it pretty well. You can try to send some mass or some perturbation from the boundary and look at the process of the collapse of the black hole, interpreted in terms of the thermalization of the boundary theory. And you will find that the entropy initially grows. There are some particular behavior that it can be more or less universal, and eventually it saturates to the thermal black hole entropy of the black hole.
So basically, I think so. Like you're saying that in a dynamical situation, a shock wave or something like that eventually collapses into a black hole.
Exactly.
Yeah, okay.
So you can try to look at the now time. This is real time, and this is entropy. This is entropy because we will need to define properly what we mean by entropy in a dynamical setting. But quite generically, in these black holes, you will see, I think there are some non-universal features at the beginning, but then it grows linearly for some time, and eventually it collapses to a black hole.
I see. Thank you.
So this plot can be done quite rigorously in the context of ADS black holes. And there are some physics in the slope of this line and in the time scales of collapsing and saturation. Yeah.
So, Imran, am I starting in like 5 minutes or?
Yes. So, yes, you are starting at 10:45. So,
Okay.
is there any other question?
Sorry, I took a lot of time from the break.
Well, today we had a different sort of tea break, so we suddenly moved online. So I think it's okay.
Yeah.
So like we can have maybe a 5-minute break, but I'll just keep this online session on, and so if there's a question, then it's okay. Otherwise, like it's a 5-minute break, and then we but join again.
Okay,
at
so
10:45.
let me then. Yeah. So I will stay here, but I will stop sharing.
Yes. Mushahid, you can
so
ask
you can
if you have a question.
Hello,
If
am I audible?
if you have questions.
Am I audible?
Yes.
Yes.
Okay, so I just wanted to ask that as these questions remains unanswered, do we have a best candidate that we can think of that could give us the possible answer to this question among the recent theories that we have?
For the particular question that I asked in
Yes,
this
yes,
class,
exactly.
that is, what are the microscopic
About the
molecules of the
microstates
Schwarzschild
of
black hole?
exactly about the
we do
microstates
not.
of.
Yeah, we do not have currently an explanation for this entropy. This is a very hard problem because the specific heat of the Schwarzschild black hole is negative. So the black hole evaporates and it's not an equilibrium situation. So it's like if you want to explain the molecules of a glass of water, but water is leaking. So there's not enough time for us to look at the water in the microscope and see its molecules. It's much more convenient if we have a system that is in thermal equilibrium, and so we have infinite time to look at the microscope and try to find those molecules. The equivalent thing of having a stable black hole is the black hole in ADX. And that one we know pretty well what are the microscopic atoms of those black holes. But Schwarzschild is an open, very difficult problem. Flat Schwarzschild.
And for ADS black hole, it's a quantum field theory that would explain these microstates, right? That's what you were telling me earlier.
Yeah, so the surprising thing about these atoms is that it seems that these atoms do not live in the same number of space-time dimensions as the black hole itself. So in the case of molecules and water, we look at the microscope, we find molecules that they live in a three-dimensional space and one dimension of time. They are molecules that live in the same space as the liquid itself. In gravity, what's surprising and very mysterious is that it seems that the molecules that conform this space-time live in one less dimension. That's why we say that black holes are holographic, or gravity in general is like a hologram. Because the fundamental degrees of freedom, those quantum degrees of freedom, first, they do not have gravity at all. They are not gravitational, and they live in one less dimension. And in these BPS black holes that I was telling you, we can actually do a proper counting of that, and we know we can get area over 4G from a microscopic counting, which is a double calculation that started by Strominger and Baffa in 1996, and that I don't think any other candidate for quantum gravity other than string theory can claim success in the way that the string theory did for these particular black holes.
Well, thank you very much, Damian. It was a very good discussion, and that concludes your part of the lectures.
Thank you.
So now I request Tibra to start sharing his screen.
So I have another question, Imran. Like the problem session. Sorry, Damian. Sorry, Imran.
Yes.
This one.
No, I thought it was a question for me. Sorry, no.
Sorry. Yeah, just 1 second. There's somebody at the door. Let me just get that.
Yes.
Other urgent question I can answer while Tibra answers the door.
I'm sure this discussion has inspired the students enough that now they'll explore further on their own, and they have got your email address and they can, contact you.
I'm now all the more interested in ADS CFT correspondence now that you told me like how it rises to areas black holes.
That's great. So then try doing my problem 2 in the last problem sheet, and you will get even more interested in ABS-CFT.
But I found the internet connection in your room to be quite okay.
Is it okay? I think there was some delay with the iPad. I was speaking faster than what the iPad was showing in my laptop. I have both the laptop and the iPad, so I was.
So my room, I figured out, is that a laptop is not connecting to the internet, but all the other devices are. So I will be using just the iPad.
Ah.
Okay.
So you won't be able to see my face because.
It's okay.
Yeah, and I just woke up, so my face is not something to look at anyway right now. So, okay, shall I share the screen?
Yes, please do.
Okay.
Yeah.
All right. Just.
I will mute myself, but I will
you
still
can.
be
Yeah,
here.
you guys can talk. All right.
And maybe if you choose the landscape position, yeah. So now we have more screen area for your writing device.
Okay. All right. So welcome everyone, and I'll try to keep track of the time because of a little bit of quite a bit of stuff to cover. So what I want to kind of start off is that yesterday we saw that if we take the view that the path, the propagator has the Markovian property, so we start at some, say, initial time, say t1, and we end at some initial time tn, and this is the space at t1, and this is the space at tn, and suppose we divide this into n minus 1 smaller segments, and the idea that Feynman had was that, well, if I think of the propagator as Markovian, then this can be written as xn tn. This is the whole propagator, but it can be written as in terms of like sum of propagators along many such paths, and if you want to end up here, we stuff like that can go there, 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 there. So here we have, for all we integrate over all the spatial slices in the during the intervals. So we have, say, d x2, that is over here, then x3, x4, xn minus 1, so maybe write it like dx n minus 1, dx n minus 2, dot, dot, d of x2. And here we have got the propagators that are for the small time intervals. So, and then what Feynman said was that, like, suppose that we take one of these paths. So suppose we take one of these paths, and if t is small enough if delta t is small enough, in the limit where this is going to go to 0, each of these factors will contribute for each of this path an action, an exponential of the I by h bar of the action that is associated with that little bit of path. So if I take one path from the initial point to the final point, so for that path, then there will be n minus 1 phase factors where j minus 1, this is the action that would be associated with this bit of path. And then this bit of path, this bit of path, this bit of path, so on and so forth. And why is this product? Because they're all coming from these factors, right? So now we can rewrite this, of course, as e to the power I by h bar summation now, j1 to n, s of j minus 1. And this is essentially like quantity, the stuff inside the summation, as the total action that we associate with that path. Okay? And now this is for one path. So if we look at the natural interpretation of the full propagator, we have to say that we have to sum over all the paths that connect us from this point to this point, but each path is weighted by the action that is associated with that path. Okay, and this is the path integral. So this is sketchy, and we can make this more precise now. And but before we do that, last time we saw that if I go to h equals to 0 limit, which is the classical limit. So if you have a classical particle, we expect the classical particle to follow the classical path between this is some sort of smooth classical path, right? And that classical path is going to be the dominant contribution to the path integral, because the interference between the classical path and its around the classical path, you've got this thing, right? And therefore, around the phases from the classical path and its neighbors will constructively interfere, and therefore it'll dominate. And if there's a path which is far away from the classical path, such as this path, say, if I vary the path even slightly, then the delta S would be quite large, so there would not be any correlation between the phases associated with neighboring path, and they will be randomly distributed, and therefore they will tend to cancel out. So this path integral thing passes the first test, that we do get the classical limit that we expected. And then what we want to do is that we want to find out what this measure is in the delta t going to 0 limit. So what we do is that we say that for small enough delta t, so when delta t is almost going to 0, we can associate And here, basically, what Feynman is doing is that he's taking the Dirac idea and he's saying that Dirac's statement that this should correspond to, this thing should correspond to the exponential of the action. Here he sets that equal, okay? But this is for a very small interval. And you see that this has the dimension of length because it's got integrals in it over space. Therefore, there has to be a normalization factor so that this expression is dimensionally correct. Okay? Are there any questions? So the normalization factor will have dimension of length, right? Now, Feynman also makes another assumption here, which turns out to be true because he knew where he wanted to get to, right? He wanted to get to quantum mechanics, and the assumption was that this normalization factor. Remember, this is a normalization factor for the infinitesimal bit. This is not the normalization factor for the whole path integral. That this is independent. The normalization is independent of the potential. So, so let's look at what this guy is when delta t going 0, and also calculate the normalization. So in the delta t going to 0 limit, what we have is that we have two of these things, and we can assume that the particle, if it's traveling from, say, xn tn minus 1, to xn and tn, that it's traveling around the straight line. So the action that we associate with this, well, the continuous version of this action is this. But now we discretize it, assuming that the particle is moving in a straight line. So the discrete version of this is going to be, there's some delta t, which is just this integral, and there's the mass m/2, and the particle's position at time tn minus the particle's position at time tn minus 1 squared, and then divided by delta t squared. So this is the velocity squared. And then we have the potential. Now the potential, do we take it at this point in time? Do we take it over here or here? Well, we basically, it really doesn't matter in the limit, but we can take it to be the average. So this is basically what is going to be. We are going to evaluate the action for a small bit using this. Now, since we assume that the normalization factor is independent of this thing, to compute the normalization factor, we can ignore. We can do it for the case where v is 0. So do it for the case where v of x is 0. So if v of x is 0, then we have from this prescription, we have xn, tn, xn minus 1, tn minus 1, one, the normalization factor, and here we ignore the V term. So here we've got a factor of delta t, here we've got a factor of delta t squared, so we can write this as I times n, xn minus 1 squared, divided by the 2 coming from here, a half coming from here, and then h bar delta t. Okay, so this is basically what it's going to be. Now, if I take the limit of this thing, where, as Taha asked yesterday, why isn't this a delta function? Well, it's not a delta function because we are in the Heisenberg picture and these are at different t's. But if I take the Tn going to Tn minus 1, so this should be small n, then we basically have the same thing as the Schrodinger picture inner product. So we expect in that limit this thing to be big xn, because then the particle doesn't really move, right? It's at the same point. That to be a delta function. So if I compare these two things, then in the t, delta t goes to 0 limit, we want this thing should become a delta function. So this is a complex Gaussian, so we could imagine, we know that, Gaussian in the limit where, this parameter goes to 0, becomes sharper and sharper, right? So this is going to, intuitively, this looks like, yes, it could become a Gaussian. But for that to be true, we need to normalize the Gaussian, right? We need to normalize it. So basically, we need to, in the delta t going to 0 limit, we need to choose, figure out what the value of this is. I'm just making sure everybody's there, yeah. What the value of this is, so that when it gives us this thing. So what do? We basically say that, well, remember that for the Gaussian, so we take we have to do some integral over one of the x's for this to be normalized. So let's write this in this way. So essentially what this guy is this factor, and we are taking one of these x's to be the integration variable. So this is a Gaussian integral, and we know what this is, but there's an I here, and you can show that Gaussian integrals can be generalized for complex Gaussian integrals. Although it's a contour integral, it gives you essentially the result that you expect from real Gaussian integrals. And so you get here 2 pi I h bar delta t over m square root. Okay. So essentially this is the normalization. So now this tells us that the normalization is 1 over w delta t will be the inverse of this, so there'll be m 2 pi I h bar delta t square root. So now we have figured out this normalization. Okay, are there any questions? So now we know what this infinitesimal propagator is. So the infinitesimal propagator is xn, let me use small n, x small n, t small n, x small n minus 1, t small n minus 1. This thing is m by 2 pi I h bar delta t to the power half, and then the phase factor is I by h bar s n minus 1, where this s n minus 1 is given by this expression. No, sorry. Okay. So now we can put all of this together in our expression for the finite propagator, the propagator that is for finite time interval. So we have x big N, t big N, x1, t1, and now we take the t going to 0 limit. So we have where is the same thing as n going to infinity limit, and there's a normalization, and the normalization is m 2 pi I h bar delta t. Now since there are n minus 1 of these factors, so the normalization is going to be, there's going to be n minus 1 factors of normalization, and then we have the integrals dx n minus 1 dx n minus 2 dot dot dx2, and then we have here the exponential, which is n goes from 2 to big N, and here we have exponential of I by h bar s of n minus 1. And this product can now be taken inside the exponential and made into a sum. And therefore, in the limit where n goes to infinity, the sum basically becomes an integral, right? So we see that, the thing in the limit where delta t is going to 0, this whole object is going to be the exponential of I by h bar. The summation will become an integral over t, where this goes from t1 to tn. And, if you look at this for a minute, well, this is just the Lagrangian. So you will have the Lagrangian, which is the classical expression of the Lagrangian, which is a function of x and x dot. Okay, so, but of course, in practical terms, if you want to calculate this thing, you have to discretize it and do it in this way, and then take this delta t going to limit, or n equals to going to infinity limit. So let me make this a bit more tidy and write this. Let me introduce the notation that Damiani has been using, which is if I go from x1 to x2, what is x1? X1 is the position at t1, and this is the position, the position at tn. And here we define the path integral, the measure, in this way. And what it means is that it's the limit where n goes to infinity of all the normalization factors times the integrals. I think there's dx2, right? Yeah. In my notes, I have a mistake. So if I use this notation, then my path integral becomes, the propagator becomes this thing. So this is d of x of t, where all the paths begin at x1 and end at xn. And here we have e to the power I by h bar. The action, the classical action evaluated on each of these paths, right? As we know, this is the classical action is a functional, so it depends on the path. Okay, so this is the path integral. Are there any questions, comments? Let me check the time. Well, okay, I think I have enough time to cover everything I wanted to say. So this is a kind of a very beautiful formula. And as you can see, this looks very much like what Damian was doing, right? Except that instead of the quantum mechanical action here, he had a gravitational action, which is a field theory action. And instead of the paths here, he had an integral over all the metrics, on basically all the fields.
So, Tibra, maybe I should ask that, like, you integrate, and your last element is dx2.
Right.
Like, shouldn't it be dx1?
No, because I want to have the x1 dependence on this side. If I integrate over dx2, then x1, then I wouldn't have that, right? So here, because because we divided it in. If you go back to the original picture, we started here. So we specified x1, and we
Yeah, I get it. Like, some textbooks use x naught, so then they can have x1.
Sorry, exactly. So you have to be careful about this counting. I understand. Yes. Any other questions? So some comments are in order. Are there questions? Please interrupt me if there are questions. Okay.
Sure.
So some comments are in order. Number one is that all the quantities inside the path integrals, all the quantities inside the path integral such as this guy are classical, meaning that they're not operators. So the quantum nature of this of the path integral really comes from this measure. This measure is really doing the heavy lifting to make this thing quantum. But everything else inside is just a C number quantity. It's not an operator or anything. Comment number two is that this is very hard to compute. Hard to compute for anything other than the simplest system. So except for, say, up to quadratic potentials. So simple harmonic oscillator is something you would be able to. So I gave you a problem. I'm not sure whose problem sheet you will be working on during today's problem session, because we have only one. But I sent a problem sheet to Imran yesterday, and where you are supposed to calculate the propagator for the simple harmonic oscillator. Okay? All right, so I have about 45 minutes.
45 minutes, yes.
That should be enough for every.
Hamas has a question, I think.
Yes, please, Hamas, go on.
So there's a simple question. So classically, let's say the action has terms like AB, where AB are just functions. Now, if one were to attempt to quantize that action, like, write it down in terms of some operators, how would that necessarily give, I mean, I'm not sure how that would give to correct theory quantum mechanically. So, for example, classically, if it's AB, maybe if you quantize it, you're not sure if it's going to be AB or BA.
Right. I mean, that's in quantum mechanics, if you do AB and BA, they would be different theories in the operator formalism. But what you're saying, I think, is that since we are in the path integral, the Lagrangian is classical, would those two theories be the same?
Yeah, will they give the same answer for both, as in the amplitude?
Right. Yeah, I don't know the answer. That's a very good question. So, I mean, I really don't know the answer. So, because the Lagrangian, there must be some way of determining this ambiguity. So, for example, theory has Lagrangian a term like this, right? Px or so, quantum mechanics, we can have xp or px, or we can have xp plus x by 2. We have these different, and classically all of these things are the same, right? So yeah, I don't know the answer. That would be the Damian, do you know? Do you have any light to shed on this?
I think about maybe I have the
Sorry?
answer by the end of it.
Okay.
Maybe I can find the
please.
answer by the end of the talk.
Yeah, please do. Yeah, thank you. Thanks for the very nice question. Okay. Any other question that we that I can try to answer, but not? Come on, guys. I asked Imran Khan to ask a question, but he's not here today. Other Imran Khan. I told him to be here, but he didn't join. All right. So, however, even though we cannot have the path integral for most systems, it gives us an insight into a new formulation of quantum field theory. And a lot of the advanced quantum field theories, such as we use today, such as, say, QCD, or these are just gauge theories, for example, and even the standard model, their quantum mechanical consistency have only been were first demonstrated using path integrals. So their consistency as quantum theory were demonstrated using path integrals. And Toft got the Nobel Prize for this, and his development, for showing that these theories, like the standard model, is actually a renormalizable theory. Okay? So, and then there are, in gauge theory, there are these things called the gauge artifacts, or the gauge, for example, in gravity, Damian was talking about the diffeomorphism invariance. And diffeomorphism invariance is basically saying that we have and this is something that I think some of the students were discussing, is that gravity, you know, when we say general relativity, what we are saying is that gravity has a huge like gauge invariance, meaning that it has a redundancy of description, that there are different coordinate systems and it describes the same physics. So when we are integrating over all the metrics in the path integral, as Damian was saying before, we have to choose, we have to do it in such a way that we do not overcount the metrics. So if there are two metrics in the path integral which are different metrics, they look different because they're in different coordinate system, but they're actually geometrically the same metric, then we have to make sure we only count it once. So this diffeomorphism invariance is a form of gauge invariance, and gauge theories can be quantized most in the best possible way using path integrals. Just kind of saying why path integrals are important. Okay. So the last comment I want to make is that, you know, we used a very sort of hand-wavy argument to derive the path integral. So, but you can show that the path integral, the expression for k leads to the Schrodinger equation being satisfied by the wave function. And most books will do it the other way. They will assume Schrodinger equation and derive the path integral. But I wanted to do something a little bit different and do it in the Feynman way, which is a lot more hand-wavy, and therefore has more of a flavor of kind of doing real physics rather than, you know, derive something that is well known. All right. So now next I want to discuss the simplest case of the path integral, which is the path integral for a free particle. But are there any questions before?
Can I try to answer Hamas'
Yes,
question?
please. Yes. Yeah.
So I think the path integral is the path integral, as you wrote it, is a generating functional of correlation functions, right? So the ordering problem will come when you will try to compute the correlation function, for instance, in what you wrote between x and p. And so in order to put that in the path integral, you will need to insert operators. You will need to insert those quantities in the path integral. And the path integral will only compute time-ordered correlation functions.
Automatically.
So depending on whether you put x first and p after, or p first or p after, you will be computing x. So it's the time-ordered correlation functions that the standard time, the standard path integral computes. If you want to compute something that is not time-ordered, then you will need to modify the contour of integration, and it will lead to other types of physics, Schwinger-Keldysh and all these, real-time dynamics, whatever.
Right.
But the standard thing that the path integral computes is time-ordered correlation functions. And there the order is just clear with the position where you insert the operators. I don't know, it's a little bit of an advanced answer, but I think that's the right answer.
Yes, Hamas.
Yeah, I think so, yeah. There's
Hamas, you want to say something?
So I partially I can understand the question, but the answer, but these operators I believe would show up as functions now in the path integral, right? If you're taking the correlations of those. But I'm a little unsure how these things that you're sandwiching between two kets, let's say Q that's being now written down, Q and P, how are those related to, I don't know, the operators that are showing up in the action?
So yeah, this thing would be essentially, you'd have inside the path integrals, you'd have here, these would be now functions, and they won't be operators. And what Damian is saying is that it doesn't matter where you put, these are still classical quantities. It doesn't matter if you put Q first or P first in the path integral. What comes out will depend on T1 and T2. If T1 is greater than T2, this will come first. If T2 is greater than T1, it'll be P first and Q. So what the path integral is computing is the time ordering. And if you want to compute something where there is no time ordering, then you'll have to do something more complicated, which involves going off to the complex plane, and then deforming the contour in such a way that you get the ordering of that you want, and that is known as the Keldysh-Schwinger formalism, and it's not I think it's a little bit, not a little bit, quite a bit outside our scope. Okay, but what Damian is saying is that the path integral will always compute when you do correlation functions, because that's what we have to do in physics. That will always, the path integral always automatically computes the time ordering, and that's something that you can show, and it's included in many standard textbooks. Okay, so shall we carry on?
Just to say that I completely agree with that formula that you wrote. So that's what I wanted to say.
Okay, so
Yes, Hamas, you.
is there another question? Yes.
I'm sorry for interrupting again and again. It's just that the problem still in my head is, there still will be some ambiguity inside the action, right?
It will be what?
The action will still have. There will be some ambiguity still in the action. Or would there? Would this?
Yeah, it'll be the same. I think what Damian is saying is that when you don't, when there are things which do not commute, that when you do the operationally, that shows up when you are computing correlation functions. Right, and the path integral is limited in being able to give you only the time-ordered correlation function. So the action will still be the same classical action. So maybe we can unpack some of this during the problem session or discussion session afterwards.
Yeah, sure. Yes.
Okay, all right, so let me carry on for the sake of time. So we are going to do the path integral for the free propagator. So the free propagator. So to do the free propagator, let me just remind you the usual Gaussian integration formula. If you have a linear term, the way we do this is we do a change of variable so that we can complete the square. And this gives us, completing the square gives us an extra term, which is b squared by 4a. And here we have square root of pi over a. So this is formula that we will need. So what is the path integral for the free propagator? So it's going to be the limit where n goes to infinity, m by 2 pi I delta t h bar, n minus 1 over t, d of x n minus 1 dot 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 dx2. And now in the exponential, we have e to the power I by h bar. And there's a summation from n going from 2 to n, big N. And here there's a delta t, which is standing in for the time integral. And now we have m divided by 2, and then 2 delta t squared. And in the numerator, we have xn minus xn minus 1 whole squared. And we don't have any potential energy term. So there's a lot of constants here. So to simplify life, let us introduce a new variable, which I call yn. So yn is just xn, but rescaled by a time-dependent factor. So we are fixing n for the moment, so we are not worried about taking time to 0, delta t to 0. So this is yn. So if I do this, then, let me just call this k. This guy becomes, so now, because we need to change the measure of the integral, we'll get, this thing will still be there, but we'll get a bunch of new constants from the Jacobian. And the number we will get is exactly the number of integrals that there are. So the number of integrals there are is one less than the number of time intervals we have, because these are integrals over the spatial slices. So there's a -2 here in the numerator. And then we have dy n minus 1 dot dot dy2, and now we have e to the power I, summation from small n to big N, and now we have yn minus 1 squared. So this looks a lot more doable. Now what we do is that we do each of these integral one by one, starting from this thing, the earliest integral. So here there are many factors of exponential. Now we have to decide which factor of the exponential are relevant here. So for the d2 integral, the y2 integral, we are going to have two factors, I y2 minus y1 squared, and I y3 minus y2 squared. Okay. So if I do this integral now, and I'm going to, for the sake of time, I'm not going to do this. You have to expand and you have to do the Gaussian integral, that you have to use this formula again and again. So if you do this, you get pi I by 2 square root e to the power I y1 minus y3 squared by 2. And now you see that why we have to do this integral first, because the result of this integral is going to influence the y3 integral. So for the y3 integral, we have to carry this thing. So for the y3 integral, we'll now have this factor of pi I by 2 d of y3 integrated over e to the power I y4 minus y3 squared, and and this is coming from this thing, which is already existing, but we carry this thing over. So we have I y1 minus y3 squared and y2. And then we do the same thing. We expand this and we do the y3 integral. And what do you get in the end? You get I pi squared. Well, you have this thing already there, I pi by 2 square root, but then you get a new factor, which is I pi times 2 divided by 3. And then you have an exponential of I by 3 y1 minus y4 squared. Okay, and here we see that these two things cancel out, and we have I pi squared by 3 square root exponential of I by 3 y1 minus y4 squared. So you keep on doing this now. And after you have done, there's a pattern emerging, so you can do one more. But after you have done the, the y n minus 1 integral, what you will get is, you'll get I pi factor of the number of integrals you have done, which is n minus 2 divided by 2. And here you will get square root of n minus 1. And here you will get e to the power I, n minus 1, y1 minus yn whole squared. So this is the result of the integral. So now if you put everything together, you actually get something very nice. So if I have k, so k is then the limit where n goes to infinity, and we had our usual factor, the normalization factor that we originally had, and this is raised to the power big N minus 1/2. And then the Jacobian factor we had 2h bar delta t by m, and that had big N minus 2 over 2. And now this new factor we have, so this is I pi n minus 2 by 2 by square root of n minus 2. And then we have an exponential, which is I n minus 1 times delta t, I'm rewriting it slightly, m by 2h bar, and now I'm writing it in terms of x now. So I've come back to our original variable. And now you can see that, this factor, very nicely goes inside here, right? And right. And then we have cancellations between these guys and these guys, right? So let's look at that carefully. So we have the limit where n goes to infinity, and here we have m over, say, 2 pi I delta t h bar, n minus 1 by 2, and over here I have 2 pi I delta t over m, and here I have n minus 2 by 2, and then I have a leftover 1 over 1 minus n. And here in the exponential, what we have is that, see that n minus 1 times delta t, that is actually the total time interval. So there what we can do is we can have I here, we can write I by h bar, and then m by 2, and here we have x1 minus x, it should be xn here, x1 minus xn squared divided by, now this thing becomes Tn minus T1. So we see that the delta T dependence drops out in the exponential. And over here we see that this thing is here, this thing is here, this thing is here, this thing is here. We should also have some factors of h bar, which I probably forgot. Yeah, so there should be factor of h bar. Yeah, there's a h bar here, right? So I forgot the h bar. So there's h bar. So everything is basically like this is just exactly the inverse of this, except that here there is one more power than there is over here, right? So all of those things cancel out. So we have n goes to infinity, and what we will have here is m by 2 pi I delta t, and now I can take this thing inside because there's only one factor of square root, and then h. And here we have exponential, the same thing. Now we see that what is this thing? This is nothing but T2, sorry, Tn minus T1. So we see that this is actually the expression we have derived in the end is actually, we can take this limit smoothly, and that's because we are in a free particle, so we don't, nothing is weird is happening here. And in quantum mechanics, we don't expect divergences anyway. So you have exponential of this Im by 2h bar x1 minus xn squared Tn minus T1. And this is the expression for the propagator, for the free particle. And you can use Schrodinger equation and Fourier transforms to derive this as well. Okay. So this is basically, I have one more topic to cover, but are there any questions about this? I mean, this is something that should be derived in a basic course in quantum mechanics, but it is not always done. So you can also derive this using traditional quantum mechanical methods. And it's not very hard. It's just a Gaussian integral. If we, I think it's a Gaussian integral you have to do there. Okay, so this is an example of how you compute a path integral, but that doesn't always work. Okay, that doesn't always work because it only works because we could reduce this problem to a problem of Gaussian integrals. So in physics, we can only do Gaussian integrals, right? We cannot do anything more complicated than that. In quantum field theory, at least. So what do we do when we have more complicated system? So we are going to use something where we can at least compute things in the semi-classical limit. So let me just sketch what we do in the semi-classical limit, and the formula that we will derive will be used in the tutorial problem that, the problem set that I've given you. So what is the semi-classical limit? The semi-classical limit is the limit where h bar is going to small. So, we know what the classical limit of the path integral is, it's going to be e to the power I, the s, for the classical path, the action for the classical path divided by h bar, right? So in the semi-classical limit, we would expect some corrections that vanish when this limit is taken, okay? Compared to this guy. So to do this, what we do is that we take an arbitrary path inside the path integral and write it as a difference as the classical path. So what is the classical path? The classical path is the one which solves this equation, the Euler-Lagrange equation, right? So this is the variational Hamilton's principle, and what follows from it is the Euler-Lagrange equation. I'm assuming you've seen the Euler-Lagrange equation. And so there are corrections to this, and the correction, we call it the quantum path. And I'm introducing an h bar, square root of h bar here for later convenience. Okay? So this is basically what we are going to do. Now the thing is that essentially what we are doing is that we are expanding our integral around some given path. So the analogy is that we are shifting our variable. So if we have an integral, say d of x of f of x, right? Then we introduce a new variable, which is x plus x naught, right? So if it's a constant shift, then the integral is just going to be dx prime f of x prime minus x naught, right? So these two are the same integral, it's just that the dependence of the function changes, but here the Jacobian is just 1. So here, when we go from integrating over these paths to over here, this is a constant path. This is not varying. So we are basically just changing variables to this quantum variable. So, and you can show this more rigorously, but here, I'm just motivating this. So the measure that we had in our path integral, which was something like this gets replaced to an integral over all the quantum correction path. Okay? So now, what we do is that we also say that, well, we also express our action. The action is as you remember, it's a functional, meaning that it's a map from the space of functions to the real numbers. because what value of action you get, it depends on the function you choose, the path you choose. So now if I expand the action around the classical path, so let me just write this as the classical path plus the quantum correction. So far there has not been any approximation done, but now we are going to do is that we are going to do a Taylor expansion, a functional Taylor expansion. It's not a Taylor expansion of the function, but the functional. Yeah?
This variation or this additional term which you've added to the classical position, how is that dimensionally correct?
No, I mean, this is not this has different dimensions. Its dimension will be determined by this thing. So I'm not saying it's actually I'm not saying delta Q has dimension of length. Okay?
Okay.
It's a rescaled, it's rescaled. Okay, so good. So if you do a Taylor expansion, we'll have the classical, so this is the action evaluated on the classical path, and then we have a linear term, and inside the linear term we'll have a functional variation of the action with respect to x of t. X of t is some dummy variable, and then this is evaluated on the classical path times delta xq of t, and this is integrated over t. This would be the first order correction. The second order correction would be square of this, and the square of this is going to give me h bar. And here I will get a second derivative of s, the functional derivative, with respect to x of t, delta x of t prime. And again, we evaluate it on the classical path, and how now we will have delta x qut and delta x qut prime, and here we have the integral is over 2 factors of dt and dt prime. And then we have higher order terms, higher order in h bar. Now you see that something interesting is happening. Because this is evaluated on the classical path, we know that for the classical path, Hamilton's principle tells us that this thing for x classical is 0. Therefore, in this expansion, this term is going to be 0. This is exactly what happens when we expand, do the Taylor expansion of a function around, say, an extremal, a minima or a maxima. And so we have chosen our h bar. We have defined this thing with a factor of square root of h bar. Now we can evaluate our path integral as a series. So our path integral, which was before like this, now becomes, it's an integral over the quantum paths. Now the leading term is the action evaluated on the classical path, and then this first order term is not there, and the second order term has h bar. So this becomes this plus I, and let me write this whole term symbolically as S double prime. And if I look at the higher order term, they will all, it'll start with order square root of h bar. So you see this thing now doesn't depend on this quantum, so we can factor this out. So it'll be 1 over I h bar, and inside we'll have d x q u, sorry, my x q u of t, and e I s double prime plus, and because, plus corrections of order that begin with order square root of h bar. Now if I take the h bar go to zero limit, which is the semi-classical limit, then this thing becomes ei, so there should be an s, let me call it s classical, although that's not strictly correct. This is going to be d of delta x q u of t, and then all these terms will be suppressed in this limit. But this term doesn't have any h bar in it. So this term is going to be there. And if you look at this term, this is a functional integral, but it's a Gaussian functional integral. It's a Gaussian functional integral. And we know how to do Gaussian functional integrals. And therefore, in the semi-classical limit, we can actually have an expression for the propagator in the semi-classical limit, and it is approximately given by e to the power I, h bar, s classical, and then d of delta x qu of t e I s double prime. Okay, so this is the semi-classical limit, and this is something we can hope to compute. We can do a perturbative expansion of this if we have a small parameter, a coupling constant, if the potential is very, very complicated. But this is the semi-classical limit of the path integral. Okay, so if you do this integral formally, you can show that this integral is the same thing as I over h bar s classical divided by, this happens to be an operator, an infinite dimensional matrix. This will basically give you a Gaussian integral, which will be, you will have to take the determinant of an operator, okay? And this is a difficult object. It cannot be computed exactly, but when you have a weak coupling constant where the interaction terms are weak, you can do an expansion of this, and you can actually calculate it in a Feynman diagram sort of method. I have 1 minute. So, yes, using the trace and determinant formula, one can write this in another form. And that is going to be, we can exponentiate this thing. And this can be written as e to the power I by h bar s classical e to the power half log of the determinant of I s double prime. And this we can then define to be exponential of I by h bar, some effective action, and then the effective action, which is sometimes called the quantum action, has a classical part and a part which encodes the quantum correction in the semi-classical limit, and that's given by this. Okay, so, and this is kind of a famous formula. However, you won't be needing this. You will be needing just this expression. You will just be needing, this expression for the to compute the propagator for the simple harmonic oscillator, which is the problem sheet that I've shared with Imran. But I will also update the web page over the next day or two, and then I will send Imran a message so he can update you, and you can have all the lecture notes and I'll include an optional problem as well. Okay, so this is where I want to stop. I know it's very sketchy, but yeah.
Right, thank you,
So
Tibra.
just a comment, because in the
Yeah.
harmonic oscillator, because the action is quadratic,
You can compute this
that's-
exactly, yeah.
You are not even taking an approximation there, right? That's the full.
Exactly, yeah. For the
pattern.
harmonic oscillator, this is, this thing is actually, for the harmonic oscillator, this is an equality. Okay, and we use this in the, so we do a trick. When you do the harmonic oscillator calculation, you can go and divide up time as you did in this case, and do all the do kind of some complicated integrals, and that's should be done. But in the tutorial, in the problem sheet, I use a trick which you can use for quadratic Hamiltonian, and yeah. But you the bulk of the calculation is calculating what S classical is. Okay, questions?
Taha, do you have any question?
Not yet, but
Okay, so
probably soon. I'll email you.
so it appears that like you have questions from the area of general relativity and that side. So
It means that I was either exceptionally clear or I have basically confused everyone, defeated everyone completely, and I won't be taking bets on which one is more true.
no, I think that's
No, it's just that I have I've encountered path integrals for the first time, so it's a lot of stuff to absorb. But I'll be asking a lot of questions to you via email, so don't worry.
Please do, yes.
so yes.
It's a very beautiful formulation of quantum mechanics. So.
Indeed. Hamas had, a series of questions, and now he has raised his questions, his hand. So,
Yeah,
Yes,
please,
Hamas.
Hamas.
Not a question, but just could you share the resource about this calculation in detail? Some book or some paper?
Yeah.
Yeah, I'll share a resource. I think the best place for path integral, in my opinion, is you either look at Shankar or, Shankar is the best place, I think. Because given your level, given for an undergraduate level, Shankar's quantum mechanics is the best place to look for these things. But I will also once I've made converted these to better handwriting, I will also share my lecture notes. I'll include the references, but if I forget, please email me and bug me, okay?
And Tibra, while we are on resources, so I want your opinion that Feynman himself has written a book with, I guess, Gibbs on path integrals.
Hibbs,
Hibbs,
yes.
sorry.
Yeah, it's a good book. It's a difficult book to read. So I recommend that you read the book. I haven't read all of it. I've read bits and pieces of it. My recommendation would is that you don't learn from Feynman. You
Okay.
read that book after you've learned it from somebody else.
Right, right.
Oh, sorry.
Yeah, I like very much, so for quantum mechanics at least, the derivation of the path integral as it's taught in the Sakurai book that Tibra also mentioned.
Yeah,
the other day.
Sakurai is my go-to. It's just that
it's very clear.
And I use Sakurai. I use Sakurai here completely. I just stole stuff from Sakurai. But what I'm saying is that Sakurai is a little bit more advanced. So if you can read, you don't have to read the first chapter of Sakurai. You can just go to second chapter. The first chapter will only
the path integral.
Yeah, path integral is extremely good there. And Sakurai will, like, the first chapter will just confuse you. The second chapter is very, very clear.
And by
My derivation is basically.
by Sakurai, you mean Sakurai and Neapolitano?
Yeah, I mean, I don't have the original Sakurai book, so yeah, the second or the third edition. I use both. I mean, I use second edition to prepare this lecture, but the third edition has more problems, so.
Yes, you told us, yes.
Yeah. So, can I give like one intuitive pull of a path integral where it's very short, but it just tells you, it gives you a very fun insight into path integral?
Yes, sure, why not?
So, so suppose that we have a screen here, and we have a source of, say, particles, quantum particles here. Or we have, say, some, waves of some particles coming as a parallel wave here. So we have a barrier here, and behind the barrier is a screen. So if these were particles, then the geometrical shadow would start from, the shadow would be here. The shadow would be the geometrical shadow, right? But we know that for optics and for quantum mechanics also, because of the way nature of quantum mechanics, we are taught that, there will be diffraction, right? That there will be, some of the light will bend around the corner. The bending of light is known as diffraction. So there's a path integral interpretation of this. And the idea is that, if you had a path going from here to here, here to here, that would be a non-classical path. So that would be quantum path. And if the screen were not here, if the screen were not here, that path, there would be other paths, say, going this way, that would cancel out that path. But because you put a barrier here, you're cutting off a lot of the quantum path. And therefore, the cancellation that would have happened if there were quantum paths, other quantum paths are not happening anymore. And therefore, the path integral gives you a very, very beautiful insight into why diffraction happens, right? So this is an example I wanted to give. And this is also in Feynman's, in the Feynman lecture, where he discusses the principle of least action. So are there more questions, or do we move on to the problem session?
Yes, like in principle, this is the time for problem session. So, would you like to share I have already shared the problem with the students on the WhatsApp group. So you can share the problem on your screen if it is possible for you, and then
you mean the problem set? Yeah,
yes,
of course. Let me see if I can find it first. Okay, let me just. it's called black holes or something. ICTP, yeah, that should be.
Like you also
All right,
emailed me if you can.
No, it's okay. I can just open it here. All right, so let me open this in Notability so that we can, if there are questions, I can actually all right, so this is the, so let me just like quickly go through the problem. So this is the, just give you the outline. This is the formula that we derived using this expansion. And what I'm saying is that for the simple harmonic oscillator, it's an equality, not approximation. And yeah, so, and then the thing is, because it's a quadratic action, you can show that, you know, this thing, this integral does not depend on xi or xf. Okay. And because of this, you know, this integral can be done using a trick. But let me just leave this here. So first, start with the Lagrangian, and then calculate the or the Lagrange equation. Okay. Okay, maybe Imran, should I just give an overview first so they can just like
Yes, yes.
yeah, so the idea is that first you, given the Lagrangian, which you should have seen in some classical mechanics course, this is the Lagrangian for a simple harmonic oscillator, so the potential here is not zero, but it's a very nice potential that we can solve. And you saw how to solve this thing for the Hamiltonian, the energy eigenvalues. And the Euler-Lagrange equation is del L by del X minus d by dt of del L by del X dot equal to 0. Right. So you use this in this to find out that this is the equation of motion. Of course, this is the equation of motion of harmonic oscillator that you know from Newton's law as well. And then verify that the most general solution to this is this superposition of sine wave and cosine wave, where A and B are integration constants. And after that, you know, just for simplicity, set the initial time to 0, final time to big T. Bring the value of T to 0 here and here. You can solve for A and B. If you eliminate A and B, you should be get as the classical solution of the classical path. And then in the time derivative of this, you can calculate X dot. So these are all easy calculation, but the next step is not very easy. You basically take this Lagrangian and put in the value of xt and x dot, and then you calculate the action, which has to, you have to do an integral over dt, and that's a long calculation, and that's how you find S classical. Okay. So once you've found S classical, you make the argument that since the second factor doesn't depend on xi and xf, why? Because you've taken two derivatives, right? Two derivatives with respect to x, so there is no x dependence anymore. So there cannot. So it only you know does xf. So therefore, contribute an overall normalization factor. So and then you know in the Schrodinger picture to be true, and then you insert a u dagger u equals to 1 in here and the identity operator to write this as k star k with different values of x prime here. xi and xi. But this we have already assumed has this expression. So if you now put in, this expression with f classical given by this, then after a bit of calculation, you can show that this object is given by this expression. Now, but the right-hand side is just a delta function. So the right-hand side, we can rewrite it, in this way. And you will find that, if you compare the left-hand side to the right-hand side, then you, in the limit where, xi is equal to xi, because that function is non-zero, you will basically, stuff like this term, exponential will go away because this will become 0. So exponential of 0 is going to be I1. You will get that, the value of n squared, and you can choose that to be the, you can take the real, up to a phase factor, n is. And then if you put all of them together, this is the expression for the propagator simple harmonic oscillator. And it's quite a famous expression. Okay, so there's difficult bit here, and this is not just long. But I've given you enough that given, maybe it'll take you, we won't be able to finish it, not maybe, I don't think you'll be able to finish it during the 1 hour we have, but you'll be able to do it maybe over the weekend. Okay. Another thing I would request you to do is that if one of you have made a solution and found the solution, can you share like a fair copy of that solution with me so that I can put it up in the course web page?
I think
and
that's
with your name, of course.
Yeah, that's a very good opportunity, and I would encourage all the participants to try solving this problem sheet especially, and sending a neat copy to.
Yeah, take your time. Yeah, and if you like, if in the end you are like, yeah, do it, then I'll post my own solution. Okay.
Yes.
But I'll wait for you guys to first try this.
So I just have a very general question, but before that, okay, let's take the question by Hamas.
Yeah.
Yes.
What's the point of calculating the semi-classical approximation? I mean, we already know the classical result. So why start off?
Yeah, you want to calculate the quantum mechanical correction to that, right? So, for example, when I showed that the light bends around a barrier, so imagine that the intensity of the particles. Let's take electrons, because light doesn't have mass. So let's see, take the intensity of the electrons in the beam to be very, very low. Such that there is only one electron at like very sparse number of electrons, right? So basically you can think of electrons as particles now, because the number of density of electron is so low, right? So then the fact that the electron, then a pattern will build up over time of on the screen behind the barrier. And so, but the pattern that you will get is the same pattern you would get from wave mechanics, but it'll build up over time. So, but the final pattern it's saying is that, well, the electrons are particles, right? So we better treat them as particles. And if you treat them as particles, then their path is, the quantum trajectory does make a contribution. Otherwise, we would not see diffraction. So if you want to calculate that, you need to go beyond the classical approximation. I mean, the double slit experiment is the thing that you want to think about here, because in some sense, the Feynman path integral is the double slit experiment gone completely crazy, right? You've just taken you're just doing the double slit experiment, there's the famous thing that if in the double slit experiment, if you also bring down the intensity of the beam so low that there's only one particle at any given time in the apparatus, then what path does the particle take? Well, it goes through both, right? And both of these paths are non-classical, or could be non-classical. But the fact that you get contribution from both of these paths is because the other paths, nearby paths, which would have canceled those paths, you're blocking them with the barrier. That's another way of seeing the double slit experiment, right? It's in analogy with the diffraction. All right. I mean, I will be here, so if you have more questions, particularly to the problem sheet, I'll be answering those as well. But
so, meanwhile, I would like to know from the participants that, in our previous previous in-person classes, there were 3 ladies. So one is Hinza, the other is Hera. Can anyone tell me the name of the other lady, because I have to get the certificates ready. So if anybody can tell me the name of the third lady, then I'll they can chat and send me directly or send in chat. Hinza, you know that name?
Hello.
Yes, Hinza.
It's one of the girls from Texas, Fariha.
फरीहा, और उनकी यूनिवर्सिटी कौन सी है फरीहा की?
From Pyas.
Okay, so the regular girls were you, Hinza, Hira, and Fariha. All right. Okay, thank you. So, Tibra, I have a question. So you are here, right? Yes.
yeah.
So, simple harmonic oscillator is a very simple thing to visualize. So when we say the propagator, so that means we are imagining that you go from one oscillation state to another, and the propagator will tell us about that.
Right.
Yeah. Okay. But I mean, it's such a complicated expression for that.
Yeah, on the mechanics. Sorry, can you hear me?
Yes, I can hear you.
Yeah, my headphones just died, so I have to switch to the audio on the iPad. Yeah, it is a complicated expression, and the thing is that we are not. I mean, so if you look at the harmonic oscillator, if you look at the ground state, the ground state is which is something which was I asked them to do in the other problem. The ground state it's a Gaussian, right? So and this doesn't look like what happens this doesn't look like a harmonic oscillator. I mean, what is happening here, right? So to get a classical correspondence, you have to go to a much higher energy state, and then you will get something like this, right? And then you can show that if you compute the and you can compute the probability from here. And if you then, you can compute the probability of the classical harmonic oscillator, and where the particle spends more time. And then there is a correspondence. There is a correspondence. I kind of forget the exact, but something like this, right? Something like this. And so the two things match up. But this is a time-independent picture, and you're like, okay, but where is the oscillations happening? And to see the oscillations, one has to ask for what are the classical analogs. What is the quantum analog of the classical particle? What is the quantum mechanical state, which is analogous to the classical particles? And those states, if you look at the time evolution of those states, I mean, this guy has energy. So, I mean, the time dependence of this thing, of this thing would be e to the power minus x squared by t by 2, and then you have e because it's an energy eigenstate, right? So it's going to have e half h bar omega t, right? So this kind of doesn't seem like, so there's an I here, right here. So, and there's a minus, so there's a minus I, H bar, but the H bar will be canceled by the H bar here. We have a factor of half here. And here you see we have oscillations, right? So, but this is an oscillation of the wave function, right? But if we compute the probability, then this guy will go away. So similarly, you can find the well, we know that this is a state which is a state of minimum uncertainty. So if I look at delta p and delta x, this will be equal to h bar by 2. And it turns out that the states of the simple harmonic oscillator, which only the ground state satisfies this. The other energy eigenstates don't. But there are other states which are not energy eigenstates which do satisfy those. And these states they are eigenstates of the annihilation operator, and they're known as coherent states. And if you look at those states, you will find that they actually, those states, they won't look like a Gaussian or anything, but those states will basically do a oscillations. Their time dependent is that they go there and then they come back, their time dependence. And there was actually a very nice website, I'll have to find it again, where there was an animation of the coherent states. So, I've never done this, but I'm assuming that there must be a way of using this propagator in the computation of the coherent states.
Right.
Well, the propagator is the time evolution operator, right? So for any state, if you want to find the time evolution, what is this? This is just x of psi of t, right? And here you would have x u of t psi at time 0. And then you want to express this as x u of t x prime psi of t, and with integral over dx, and here you have the propagator, right? So that's where the propagator will come in. Okay. So when you find the a of psi, you find the solution of this, right? But then you will be given, the answer to this is actually known. It's a Poisson distribution over the energy eigenstates. But once you've done that, to actually do a space calculation, you have to use the propagator over here. Right? So I just answered my own question.
Right.
But there are other ways of doing this, which is simpler. But the point is, you can do this with the propagator as well. I mean, it's the same calculation, but so essentially, giving this formula means that we have the general time dependence of the harmonic oscillator at our fingertips.
Right.
All right, any more questions?
Well, I would also like to ask that when you write the effective action,
Yeah.
which is the classical plus some terms, so
Yeah.
I was just wondering that can we say that effective field theory is related to the effective action, and I mean that's a full theory, but is the essence is the same? That
I think effective field theory is something different.
okay.
I think, unless I'm wrong, Damian, you can. No, I think it's kind of the same thing in some sense. I've never
Maybe
connected these two.
you can explain the effective action, again for me,
Yeah. So, right. So, let me go back to my other thing.
I mean, in a way, it is straightforward that it is the classical action plus some terms.
Yeah.
Yes.
So this is
Hamas,
kind of more of a
do you want to contribute?
Yeah, maybe I can make an attempt to explain how it's related to the effective field theory.
Please do.
Is that okay?
Yeah,
Yeah,
sure.
of course.
So if we talk about, let's say, a gravitational theory, an effective field theory just means that you're adding more actions or more terms to the Einstein-Hilbert action. So if you were to write down, so these would include terms that Dr. Damon talked about initially. Other scalars like r squared and square of the Riemann curvature tensor and so on. So if you were to write down an S effective for that theory, all of these additional terms would just be included in S classical. And then if you were to quantize the theory, then we would have to add this log S double prime.
Yeah, I think what I've seen of quantum gravity, and Damian can correct me if I'm wrong, is what you call classical and what you call interacting terms. There is no, I agree with you, but here, we are expanding our own classical solution. That's the point. And
Yes, so it is an expansion.
yeah, it is an expansion. It's a leading order expansion. In terms of the coupling constant, in terms of H bar. Sorry, Damian, were you saying something?
No, but I can go afterwards, so you can finish.
No, please. I was just thinking aloud, so please go ahead.
Yeah, so usually, I mean, what we are still not talking about here is the energy scale. So the theory tends to change as we change the energy. And what we usually call the effective field theory, it's usually when we start restricting our energy scales up to a certain energy. We say we integrate out the high energy states, and we are left with a low energy effective theory that describes the system up to a certain energy. Okay?
Right, that's the effective field theory picture.
Yeah, so here it's a little bit similar in the sense that we are taking H bar as our cutoff in a sense.
Right.
And we are when H bar becomes sufficiently large, then we will start needing to incorporate all the other corrections to the action.
Yeah, so this is strictly perturbative, the effective action here.
And Tibra, when you say leading order expansion, can you explain? So what's special about it?
The word leading order is used interchangeably with second classical.
Okay.
So leading means that it's the first order corrections in powers of H bar.
Okay.
To the classical computation.
Okay.
But even that cannot be exactly computed. That can only be, this thing is a formal expression. To compute this, you have to, if, for example, our Lagrangian is not quadratic, this S double prime, the trace log of S double prime cannot be computed exactly. It has to be calculated in a perturbations theory. So we have to then do all that song and dance about, what do we call the free theory? What do we call the perturbation or the interaction? And then we have to have some sort of small coupling constant with the right dimensions to have an expansion, and then we can do Feynman diagrams to calculate that in that expansion. And then we will just pretend that expansion actually converges. In quantum mechanics, that expression doesn't converge, but the terms are finite. In quantum field theory, that expression doesn't converge, but the terms are infinite. So you have to do an extra step called renormalization or regularization, and that's where effective field theory idea comes in, because when you're doing regularization, you have to introduce a cutoff, and if that cutoff is something that is kind of physical, that is an intrinsic part of your, for example, if you're dealing with phonons, you know that there's a microscopic description but you're not interested at that length scale. You're interested in a higher length scale. So there you have the cutoff, and then the phonons will be an effective, the theory of phonons will be an effective field theory. So here, there is the expansion in H bar, but there's also an expansion in lambda, the coupling, right? So that has to be done. So to compute this trace log, you have to do an expansion in lambda, and that's where Feynman diagrams come in.
Right. So, like, the expansion is similar to, I mean, it's a Taylor kind of expansion.
No, this is a Taylor expansion. This is the Taylor expansion. That is more like in quantum mechanics where we do perturbation theory, we just take the Born approximation and we don't do anything else afterward that. That is, I don't think of the Feynman diagram as a Taylor expansion. It's actually more, it's more complicated than that, right?
Okay.
It's a quantum mechanical correction which seem to have where the Feynman diagram gives you an intuitive way of to do the accounting for all the terms.
So you can think of it as an expansion, as a Taylor series expansion in your coupling. I mean, not Taylor series because you're not expanding a function, but you're doing right. Each vertex will come with a G or whatever, and higher loop diagrams will have higher G powers, and in this sense, it's an expansion for small G.
Okay, yeah, no, you're right. But in Taylor series, we usually find the terms are converge, but yeah, you're right. It's a formal Taylor series expansion, yeah. Because
it's an asymptotic series, but
yeah, it's an asymptotic series, yeah, okay. Thank you. So yeah, you're right. It's a Taylor series, but in lambda. Yeah. We are expanding it around the lambda equals to 0 point.
Right.
Yeah, exactly. So that's why the propagator usually is the free propagator, and then you do whatever vertices and loops. But
exactly, and they are basically, the corrections are Taylor series corrections. You're right, in terms of free propagator. Yeah. Thank you.
And there are powers of H bar also.
Yeah, those can be shown to be related to loops.
Okay.
Because the number of vertices and the number of loops are not always the same. And the Taylor series, the lambda is more related to the number of vertices.
Okay, so there's a question for Dr. Damian. You are mute, Damian. Please unmute yourself.
Sorry. So there are some nice notes by Tom Hartman, who is a professor in Cornell, that has very nice notes on the gravitational path integral, the Euclidean path integral for gravity. Let me find them and I can send the link.
Yes.
Those are really nice notes.
Yeah, and he also has some lectures. He has some lectures online that you can look in YouTube that probably he explains much better than me. Let me try to find them. So it's this is the particular chapter on the gravitational path integral, but you can
Okay,
also
let me unshare so you can share.
Oh, I'm just sending the links on the chat.
Okay, all right.
But in general, so I sent the PDF, And then I also sent the website where you can find all the PDFs of it's a longer course, and it also has problems. So if you want to practice from there, that's a nice resource.
Right, thank you. So while we are discussing the experts in the field, I just recall, I would like to ask, like, if any of you is familiar with Nick Warner. I found some of his lectures on YouTube. So I'm just asking generally, have you met him? You know him?
Yes, I know him.
Okay.
But yeah, but what's the question?
No, there's no question. Like
he's a professor now. He's a professor in Paris now. He used to be in the University of Southern California in Los Angeles.
I mean, he works in
He works on something called the fastball program.
Yeah. But fastball is something out of our scope.
Something out of?
Our scope. Beyond the scope of our lectures.
Yeah, I can tell you. Yeah, it's a little bit more advanced, but yeah, so the next step, if I had to give another 1 week course on black holes and thermodynamics, would be to tell you a little bit about the black hole main paradox. That is the fact that it seems like Tibra told us on one side that unitary evolution does not destroy information, in the sense you can go back and forth, t and minus t, and you will recover what happened before. But black holes are a little bit strange, in the sense that if you send something in, no matter what, once they fall inside the black hole, the only parameter to describe it is m, the mass of the thing. It doesn't matter whether you threw the Britannica Encyclopedia or if you threw a cow with the same mass, you will have the same black hole. So it looks like when you try to put the concept of unitarity in contact with these ideas of black holes, there seems to be a problem, because there seems that you are losing information about the system when it falls into the black hole. But we know that the black hole evaporates, so one might think that eventually when you recover all that radiation, you might be able, even though it might be a super hard task, you might be able to find again all the information about what made the black hole. However, the radiation is thermal, so it means that it doesn't carry enough information, and that leads to what we call the black hole information paradox. That it seems, if radiation is thermal for all times, that eventually the black hole will completely evaporate, we will get all this thermal radiation, but we will lose all the information about what formed the black hole in the first place. And this violates the unitarity of quantum mechanics. So this is a big paradox in theoretical physics. No one knows the answer to it, except in very particular scenarios. And the fastball program, what proposes is that actually, at the quantum level, there is no black hole horizon. If you look very close to the event horizon, you see that there's no event horizon at all. There are some fuzziness that comes from quantum properties, but there's no horizon at all. So what you should actually count is so from the outside, it looks like something funny is going on, but there is no actual event horizon where you lose information. And the idea is that maybe those geometries, if you manage to count them, might account for the entropy of black holes. But again, they haven't succeeded in this task yet. So I can tell you. This is a nice idea. It might work. There are some counting of these fast-world geometries, but they are never enough to account for the whole entropy of the black hole.
So what is it called? First world?
Fast-ball.
Fuzzball, okay, yeah, fuzzball, okay, yeah. Samir Mathur, yeah.
Yeah. So Samir Mathur, Nick Warner.
Yeah, okay.
Joseph Vega, all these people are trying to change the regular black hole horizon for something is more fuzzy, and that's why the name fastball, and try to say that that might solve the information paradox because there's nothing coming in and out of the black hole. It's just a fuzzy ball, but there's no black hole. But again, it's a highly speculative idea. It's nice, but we cannot say that solves the information paradox, neither that it counts the black hole entropy, because we don't have any concrete realization of this idea.
How would one move from this entropy idea to actually predict Hawking radiation? Like we calculated the formula for entropy, like how did they proceed from there to get to the Hawking radiation?
Yeah, so that's a very good question. So you can think that, okay, so there's the concept of energy, right? The mass of the black hole, you can relate it to the energy of the black hole by doing, yeah. So there's a formalism in gravity to compute energies that goes under the ABM formalism, and you can think that maybe this mass of the black hole is actually computing the energy of the black hole. Then you have these area theorems that say that the area of the black hole can never decrease. So then you can associate the entropy, the entropy of a black hole to the area of the horizon. And we saw that the area of the horizon goes like mass squared. And now you can use the thermodynamic relation, ds dE is actually 1 over T or T. And you can say that, okay, if there is an energy and if there is an entropy, then it has to be a temperature that will go like 1 over the mass of the black hole. This is what people did in the early, well, in the 60s, probably early 70s. Bekenstein in particular. And then Hawking came and said, this is nonsense. There cannot be a temperature for black holes because black holes should be radiating them. And so he came up with a calculation that you can do, again, in this semi-classical limit that Tibra was talking about, where you consider the gravitational background to be fixed as the black hole background, and you consider some quantum fields on top of that background. Here now the theory is Lorentzian, everything is perfectly fine and well defined. There's a nice semi-classical limit where the gravitational fluctuations decouple from the quantum fluctuations. And you can do this computation that is a scattering computation from particles coming from minus infinite time. They do some scattering very close to the horizon, and then they go away back to the asymptotic future of space. And what Hawking found by doing that calculation in the semi-classical regime is that actually what you were finding at the end of this process is that the observers that were receiving the result of this scattering process were receiving thermal radiation with a temperature that was proportional to h bar and inversely proportional to the mass. So that gave credibility to this idea that, okay, ds dt has to be related to temperature. It's a very nice computation, but you need some knowledge of quantum field theory in curved spacetimes. But it's completely You don't need many assumptions in order to do that computation. It's a little bit harder because it needs more advanced techniques. But you don't need to complexify time, you don't need to take anything else than G Newton going to C.
And
Yeah,
Hawking
this,
has two papers, right? He also does it in the path integral and also in the canonical formalism.
Yeah, in the path integral is this paper by Gibbons and Hawking.
Yeah.
This is 77. It comes after the paper, the famous paper of Hawking radiation. But you could complain about all these Euclidean methods of being some black magic, but the original Hawking calculation is completely standard Lorentzian process where you just take G Newton to 0 and you compute the leading order corrections coming from fluctuations of quantum fields. So all that together makes the field of black hole or space-time thermodynamics credible. And now we abuse a little bit of the Euclidean path integral because it's very nice, elegant, and it gives the nice results. But we should probably be also thinking about the Lorentzian interpretation of these things. So for instance, the fact that the black hole evaporates and there is Hawking radiation, we associate with the fact that the specific heat in the Schwarzschild black hole that we obtain from a Euclidean path integral is negative. So in Euclidean geometry, there's no black hole radiation because radiation is just null, and there's no null directions in Euclidean space, but we can find hints of that by analyzing the sign of the specific heat.
So there is another problem like with quantum field theories in curve case, and I don't know if you consider it a problem, but like for a beginner like me, when I studied it for the first time, I mean, didn't really study it, but just looked at it. So there is this concept that even the existence of particles become relative. Like, doesn't it go against the spirit of relativity itself? Like, you know, there should not be a preferred frame of reference. Like, how would one hold this principle if the existence of particles itself become relative?
Yeah, it is it is confusing. But so the problem is the concept of particles and how to define a vacuum state in a curved space-time. That's the basic problem, and it's true that different observers observe different numbers of particles, especially in space-times that do not have a globally defined time-like Killing vector. So you cannot uniquely define the concept of energy. So then it doesn't make too much sense to ask what's the lowest energy state in a theory that doesn't have energy well defined. So yeah, it's a confusing field, but it's the price to pay if you want to start putting relativity and quantum theory together.
So are theoretical physicists really comfortable with this? Like, what are your personal opinions?
Well, you shouldn't be comfortable with anything, because if you are comfortable with things, it means that you are probably not pushing the field enough. So the fact that there are confusions and that there are questions that remain to be solved should be taken as a good sign, not as a bad sign. Because if we understood everything, then we wouldn't have a job either.
But it shouldn't really stop you, right?
The fact that there are tensions, it's that you are starting to feel the tension that there is between a classical theory and a quantum theory. But that doesn't mean, so the semi-classical limit is a well-defined limit where you can do computations, and then it's a little bit, you should be careful in how you interpret those computations and which ones make more or less sense. But mathematically, it's a well-defined computational framework.
All right, so I think we can end this session here, and I assume that the participants have also done some problems in this session. So we had a good discussion. So in the afternoon we have a meeting with ICTP's Natasha. So we'll use the same link, but I'll send a reminder to the participants as well as to Demian and Tibra. And so right. So
Is it at 2?
It is at 2:30.
Okay.
So I'll send a reminder also. So we can, end this meeting for now, and then we will have that last session with Natasha at 2:30. And it's, especially for the students, she'll discuss the prospects that students have in, ICTP and other international opportunities. So let's end it here, and we'll meet again at 2:30. Okay.
Cool.
So I'm ending.
All right. Thank you so much.
Welcome. Thank you for your time.
Yeah.
Damian, Tibra.
Thanks everyone. Very interesting questions.
Okay.
Keep going. It's an interesting subject, so there will be lots of questions.
Bye.
Yes.
Bye.
Bye-bye.
Bye.